if you take a look at these two numbers, now we're starting to get into some of that analytical piece that we're going to be working on the rest of the unit. And then we're going to be using all year long. Are those two numbers listed there the same? No, obviously, I would hope that we can all agree that no, they're not the same, right? Because they're different numbers. But there's two big differences that I want us to kind of be able to think about. Who can take 10 seconds or so, look at those two numbers, and then raise your hand if you can tell me one of the two big differences between these two numbers that are there. Two big things that we should hopefully be able to see with that. Jonah, give me one. One of them is pi. So talk to me about pi. What do you guys know about pi? It's what? It's an ongoing number. It never ends, right? So it's got an infinite number of decimal places. Does the other one go on forever? All right, so we can see that one of the differences is how many decimal places they have. Okay? That's a big piece, to kind of a clue within it. Caleb, what's the other difference? One has units, right? So, guys, that's the first thing we need to be able to look for, is that how measurements are different than numbers, okay? They are different in those two ways. Measurements, we said, you should be jotting these down in those bullet points, okay? One of the biggest things you're going to hear me harp on all year is measurements have units. Why? Because they represent an action. All right, that's the key here, is that measurements represent an action, that somebody did something. So that first number up there is the measurement, 3.25 centimeters, bless you. Somebody, somewhere, measured something. They used a ruler, they lined it up, they put in some effort, and they found it to be 3.25 centimeters. Pi keeps going and going and going. It has an infinite number. Can measurements have an infinite number of decimals? Can we just put up as many as we want? Absolutely not. All right, we're going to talk this week about these things called significant figures. Okay. The other piece, since somebody is doing the work with a measurement, they have built-in uncertainty. That means that if I measure one thing, you may not measure it exactly the same. There's some sort of estimation that takes place in that. I'm sure you've heard the saying before, measure twice, cut once. You ever heard that? Like when you're building something? Have you guys ever tried to build something and you think you have it right? You go to cut the piece of wood or whatever it is you're working with, and you go to put it, I got this, and then all of a sudden it's like half a foot short or it's off. It's the worst feeling. I've been working on building a table lately, and I've had to make cuts twice. I'm like, are you kidding me? Like, it's just driving me crazy. Measure more than twice, all right? Always make sure. But that's, again, that built-in uncertainty. You can think that you've got it right, but we're human, right? We make mistakes all the time. Now, if we take a look here, I'm telling you that this is the measurement number. It's got units as well because it tells us what we did, all right? So the importance of having units is it tells us what we did, all right? Write this big, highlight it. Very rarely will there be a time where you don't give me a unit. I will take points off more this year for not having units with your numbers than probably anything else. And it'll be something I consistently have to remind you of throughout the entire year. Units are important because they give us some insight into what was measured. So if I look at centimeters, what type of measurement did I make there with centimeters? So what are the types of measurements we can measure? What are the length? So that's like a distance measurement. What else can we measure? Volume. Height would be a distance. Mass. So we got distance, we've got volume, we've got mass. There's a couple others. What's that? That would be volume. Good units. Time is another piece. All right. Speed could be another piece. All right. So they give us some insight. within this number right here, what do you think, which digit is the uncertain one? What? Why do you say 5, Michaela? Absolutely. Okay? The last number is always going to be your uncertain one. That's where the estimation comes into place. So if I were to measure out an index card and I thought it was 3.25 centimeters, you might think it's 3.24. You might think it's 3.28. There's some wiggle room. That last digit's always going to be the estimated one. You're going to practice this in lab on Thursday. Okay? Again, shouldn't be anything brand new to you guys, but we've got to kind of drive that home now that you're going to be making measurements all year. You've got to have units with it because it gives us some insight into what action you did. All right? So, the next logical step for us is to talk about accuracy versus precision. Take a look at that first target right here. So you got green dots on there. Are they accurate, would you say? No? Why no? They're spread out. What about this one? Are these accurate? Not at all. What about over here? Little cluster. Oh, cluster's a word that I want us to think about. What about these? Now, this is for, golfers out there. Is that accurate? Well, okay. What's precision then? Like, are they precise? So if you said they're not accurate, so pretty much none of them you said were accurate up here. I would disagree. I would think that there are some up there that are very accurate. All right? What does accuracy, so I say that. If I said, hey, there's accuracy within this target, this middle one right here, is there accuracy? You're shaking your head, yeah, Sarah, why? Why do you say that? Okay, so she now said if you're focusing on getting to the middle, you've got one that's right in there. It's in that bullseye region, right? Absolutely. But some of them are not. So within that kind of definition, guys, that idea, what does accuracy have associated with it? What does accuracy have to define something as being accurate? How do you know if you're accurate or not? Ooh. You're onto something there. Hold on to that thought, Alora.
Is it like if all of your points are close together, it's more accurate?
Ooh, you and Alora think of the same way. Not exactly. You're aiming, guys. That's the key. Accuracy is when you're aiming at a specific target point. Okay? You're not looking at multiple. Accuracy is dealing with one piece. All right? So that's why I would say that this middle one has accuracy because this one piece, we're looking at a single piece when we talk about accuracy. Now, there's another term that you guys were throwing out there, the group. Or if you're close to everybody in the class, what's that known as?
Average.
Could be an average. What'd you say? That's precision, guys. There's the difference between accuracy and precision. Accuracy, you're going for a target point. Precision is repetition. All right? Now, this last one here, if I was a golfer, I would say, yeah, I'm pretty accurate there because I'm on the green. All right? But what am I going for really is the cup. So it also depends on how you define it. What are you aiming at? And that's what's dealing with accuracy. So accuracy is how close a measurement comes to the actual or true value. You evaluate it by comparing it to the correct value. So you look at your measured value and you compare how close it got to the correct value. Accuracy has to have some outside definition to it in order to deem it being accurate. Add to accuracy, it's looking at a single data point. So you're looking at one point at a time. When you start to look at and kind of incorporate a big set of data, that's where you're looking at precision. Okay? Now, the two go hand in hand, but there's a fine line between them. Precision is the measure of how close a series, that's your key word, a series of measurements are to one another. So you compare two or more repeated measurements. And we can see that there in our target. It's precise because the grouping is very close together, but is it accurate? Going for that bullseye? Not really. Add that to precision as you want it to be reproducible or reproducibility. Okay? Reproducibility is key when we talk about precision. Alright, so when it comes to evaluating accuracy, we don't really evaluate precision. We would look at multiple pieces and run the same test each time. But when it comes to accuracy, guys, it's percent error. Believe that you did a calculation like this on your lab that was due today, I think. You have this on your reference packet. Take a look. Get them out. If you don't have your reference packets, flip to table T. Percent error is the third formula that is listed there. One change I want you to make on your reference tables are these lines right here. What do these lines mean that I'm drawing in? Absolute value. What does absolute value mean? Can't be negative. You're going to make it positive. Now, we could have a negative percent error, meaning you've missed the mark, you're short of the mark. But we're going to make it positive, okay? I'm just going to keep it simple. Now, these terms may change. If you look at your formula in table T, it doesn't have the same values that I have, the same terminology. What do you think correct means in terms of what you see on table T? Accepted. Okay, they mean the same thing. What do you think your value then means? Right, that's your measured value. You've got to remember that on the bottom has to be the accepted or the correct or the true value. All right, that's the... In lab, you weigh a sample and find the mass to be 28.9 grams. The correct mass is 27. Calculate your percent error. You will see me work problems all year long where the first thing I do, guys, is extract the important information. You don't need all the information in the word problem. So I highly recommend setting your problems up like this. So we're looking for percent error. That's what I'm trying to go for. That means there's two pieces I need to have to solve for that based on my formula. I need to have my correct, and I need to have my measured value. Which is which?
28.9 is yours, and then 2.7 is the right one.
So, absolutely. 28.9 grams, make sure you have your units. And then 27 grams would be your correct. Now you just plug and chug. Correct? 27 grams minus 28.9 grams divided by the correct, which is 27. Absolute value means it's not going to be negative. Go ahead and do the math. What do we get for an answer? Just shout it out.
7.04.
And then our unit here is going to be percent. Okay, so percent error, the unit is percentage. Grams would have canceled out when we divided. Now we'll talk, guys, later, like I said, tomorrow and into Thursday, about where do we round. Right? There is a very specific set of rules as to how we round in our class, but for now, 2 decimal places is fine. Should be pretty easy, pretty piece of cake for you. Go ahead and try the you-try problem. When you plug in your values, 3.21 minus 2.54, the key again is to make sure you have the correct or the accepted or the true value on the bottom, not the measured value. What do you get for percent error here? Should be pretty big. What's that? Is that an acceptable percent error? No. If you got that, you would be redoing that in lab. What about the other one over here? Is that okay? Yeah, that's typically okay. Less than 10% is what you want to shoot for. I know there are some cases where people will get larger ones depending on the type of research you're doing. In a research setting, they typically will have larger ones maybe sometimes when it's new. All right. Questions? I'm sure you guys have done this before, right? So it should be review. Really quick refresher on scientific notation, something we will use a whole lot. In that little box, you kind of have the notes there, guys, kind of talking about scientific notation. So just as a refresher, this is the general form that it takes. that number out in front where the M is. Okay? It's greater than or equal to 1, but it's less than 10. Okay? So you're going to have one number in front of the decimal out in front. N, your exponent, is the number of places it needs to be moved. You guys have used this over and over. The key here to remember, if it's a large number, N is going to be positive. If it's a small number, N should be negative. Now, if it's a positive number, which way do you move the decimal place when you're going from scientific to standard notation? Move decimal where? Heard somebody say it? To the right. Think about it. You're making it a bigger number. Okay, this is when you're going from scientific notation to standard. And if it's negative, you're going to move the decimal to the left. When you're going from standard notation, scientific notation to standard notation. All right. So if it helps you when you're going through and writing scientific notation, put it in box form like this, where this could be like 2.4 times 10 to the minus third. All right. What would be that number if I were to write that out into decimal form? Would it be a big number or a large number? Sorry, big or small? Small, because it's negative, so that would be your number there. Okay? Take a few minutes. Go through. Review this with you. Try it on your own. Check with your partner, and we'll come back over the answers, and I'll give you guys your homework.